Alright, so this is the initial electronics design for the Chef Robo 2025 robot. I ended up having to change some things last minute for reasons that I would have discussed in other videos, but let's just kind of go through this. So this is kind of electrically the most complex system that I kind of achieved here. So yeah, the first thing to look at, maybe I'll kind of zoom in. So I'm using the ESP32. I initially was using an Arduino Uno, but I kind of ran into issues with not having enough RAM to run my program, so I need to upgrade. So I'm using two time-of-flight sensors. These are to detect if you don't know what time-of-flight sensor is, it basically detects the distance that an object is away from it. So I was able to use these to kind of determine how far away the platform that moves up and down is, and I needed two because that allowed me to also maintain some sort of level of balance. In the end, these sensors ended up being too unreliable, and that was the main reason why I had to switch away from using them. But for this kind of initial electronics design, I had them in use. So they use the I2C protocol. So I did not include the VCC or ground wires for all of the parts just because it would be too messy, but you can imagine that those are connected. So of course there's a clock, and then there's a data line, and then there's an X shut line, which allows me to activate one at a time during initialization, so I can give each a unique address. And then there's the GPIO lines, which kind of tell my board when they're ready to make a measurement. So that's those parts. And then next we can move on to the NEMA 17 stepper motor. So these motors, I don't know if you've ever used them, but they're absolutely fabulous. They really saved my project because in the end I ended up replacing other motors with this NEMA 17 because it is actually very accurate with its step count, and is actually the motor that is used in a lot of 3D printers, so I think that speaks for itself. Anyway, to wire this up, I kind of had my A4988 board. There's a step and direction pins, which kind of information comes from the ESP. So of course the direction tells the direction which motor to spin, which direction the motor should spin. The steps kind of tells it when it should make a step, because stepper motors, they have discrete steps. So my board might know that it wants to do 3,000 steps. So every time it wants to do one of those steps, it will send a pulse there. There is an enable, because I was having an issue where, and I guess this is why the enable is there, where the board would kind of cause some sort of currents to go through, and then you'd hear the motor like wiring a little bit, but kind of having the enable to shut it off and enable it when I need it works great. Yeah, I used, kind of as the diagram shows here, a capacitor between my 12-volt input, just kind of smooths out any sort of disturbances or any sort of voltage differences. Yeah, and then there's the 4 stepper motor wires, the 2 coils, A and B coil, going into the NEMA 17. Okay, on to the next thing. So this is where it gets a little more funky. So I have this motor driver here, and I'm actually using one motor driver to connect 3 motors, which is a little fancy. So I have these 2 vertical motors, and those ones are kind of straightforward. So I have my board, and then I have the pins on the input pin side, which connect to this board. This board tells these pins which motor to turn and which direction. So of course there's the high low. I guess there's 4 pins, 1 for each of these outputs. And yeah, that kind of allowed me to control these 2 vertical motors. But interestingly, in order to control a third one, what I did is I connected the power supply to these MOSFETs. And if you don't know what a MOSFET is, it's quite an important electrical device. It basically is an electronic switch. So you can see that each of these MOSFETs on the G, standing for gate, they connects to my board. So there would be code that turns on those gates, and then when those gates are on, current can go through. So I'm actually able to power this third slider motor using this power source here. And then of course you might mention that when I'm doing this, it's also going to move this motor. So I kind of had a little bit of a script where this motor would reverse whatever it was forced to do when this motor was moving. Yeah, so this was definitely a little bit of a fancy setup there for the slider motor. And yeah, that's kind of all the electronics. I perhaps will add an image to this video of a picture of how messy all these wires were. You can imagine it's quite messy, especially in this diagram. I've removed a lot of the kind of obvious wires, like the 5-volt and ground wires to all these devices. So it absolutely was a chaotic mess. And given that my robot is kind of moderately sized, Some wires needed to be over a meter long. And a lesson learned with this project, I was being pretty lazy and using a lot of jumper wires and a lot of like pin connected wires. So there's a lot of these wires that are just chained together, and then as my robot would move and jerk around, some wires could become detached, and it was extremely frustrating to always be trying to reattach these wires and trying to determine where a connection had been lost. But yeah, that is the initial electronics design. Yeah, so a few points. So here's a bit of a picture of all the electronics jumbled together. This is after I kind of disassembled things. So it's a little bit messier than it would have been earlier, but you can see that the number of wires is just disgusting and very inefficient. Definitely some cable management to be learned. And then this next slide here, this is the time of flight sensor that, and you can see it's glued right onto the frame where the just DC motor was sitting. So that's kind of how I had things set up there. And then just one more comment as well. So I'm not exactly certain if this was the issue, but it's possible that one of the reasons my sensor was being so inaccurate was because of interference coming from the big like 1.5 amp 12 volt motor current that is moving through the almost parallel wires to the motor versus the time of flight sensor's smaller voltage data line, so it or clock even. So it is possible that there was some noise affecting those wires. So also maybe something to learn for me about maybe wrapping my wires in ground wire or taking on some other strategy to electrically isolate my systems. But yeah, and I did allude a little bit earlier in the video, but just those inaccuracies made my robot non-functional. So I was required to take a new approach electromechanically to try to generate that accuracy that was missing.